Firstly, it's important to check that the centre of gravity can be accurately determined physically. A simple method for this is to measure the weight under each wheel, find the moment that each weight creates, sum together the moments, then divide the total moment by the total weight to get the estimated CG position. The results can be seen on screen now. It can be seen that the error is greater towards the neutral point, perhaps too great to be considered an adequate estimate. However, the further forward or after the neutral point that the CG is placed, the smaller the error. Error values below 10% should be considered an adequate estimate. This figure shows the linear relationship between the thrust and the RPM. This section displays the controls of the aircraft in accordance to Table 1. Here we can see the changing angle of attack per elevator input for different CGs. It can be seen that the further aft the CG is, the more dynamically unstable the aircraft becomes, shown by the increase in overcorrection of angle of attack per elevator input as CG increases. This happens until 40% of the mean aerodynamic chord, where prolonged elevator input causes the aircraft to lose stability and it stalls. At 50% of the mean aerodynamic chord, the elevator angle simply has to be large enough to cause stall. These figures were taken when the aircraft was operating at 19 meters per second, which is listed as the manufacturer's cruise speed. When changing the airspeed, it can be seen that the lower airspeeds reduce the dynamic stability of the aircraft, shown by the decrease in the overcorrection of angle attack as the airspeed increases. The rate at which angle attack changes is proportional to the airspeed. It can be seen in these figures that as the airspeed increases, the roll rate also increases, shown by the increase of peaks as the figures move from left to right. Each peak represents each time the aircraft has rolled. The figure on the screen shows that in order to achieve a zero thrust pitch coupling, the vertical position of the CG must be at the 0 point, which is level with the thrust line. Next we have the figures from the wind tunnel test. The first figure shows the lift coefficient plotted against the angle of attack for different flap angles. It can be seen that increasing the flap angle increases the lift coefficient, and the max lift coefficient is created at an angle of attack of approximately 15 degrees. The middle figure is the drag polar, and it can be seen that after a CL value of 1, there isn't any further increase in lift for an increase in drag. CD0 can also be seen as approximately 0.02. As for the lift to drag ratio, we can see that the maximum value occurs when CL is between 0.4 and 0.5. This when alpha is between 7 and 9 degrees. Any further increase in alpha dramatically reduces the L over D ratio. It should be noted that for all wind tunnel tests, the aircraft was operating at cruise speed at a CG location of 35% the mean aerodynamic chord, which is listed as the manufacturer's default. The figure on the screen shows the moment against lift coefficients for varying elevator angles at the default CG position and at cruise speed. The advised elevator trim angle would be approximately 5 degrees, as the green and dark blue lines, which are 10 degrees and 0 degrees respectively, cross the axes either side of the 0 point, which is the ideal point. This is so that there is no pitching moment whilst in trim. When varying the CG, the ideal position would be the one that produces the least variation in pitching moment. Therefore, the advised CG position would be between 0.125 and 0.15, as shown in the figure on screen. Provided that the speed isn't too high, the nose gear, steering and rudder inputs provide sufficient authority when manoeuvring the aircraft on the ground. However, if the speed exceeds the minimum unstick speed, which is approximately 21 meters per second, then the aircraft will take off without any excessive rudder input or even a bump in the ground. This is even without flaps deployed. With the flaps deployed, the speed needed for takeoff is 18 meters per second. This is greater than the stall speed of 10 meters per second. Therefore, when operating the aircraft on the ground, it is advised to act with caution and to keep the speed of the aircraft low so that it doesn't take off unexpectedly. Here we have the aircraft travelling at approximately cruise conditions. In order to maintain cruise conditions, the RPM should be set at around 20 and the angle of attack should be maintained at around 5.4 degrees. The lowest trim speed that was seen for the aircraft was approximately 18 meters per second. This was at an RPM of 0 and an angle of attack of around 5.6 degrees. This is beneficial as it is far above the stall speed and therefore reduces the risk of the aircraft stalling. The highest trim speed was found to be 71 meters per second, and this was at a max RPM of 100 and an angle of attack of 1.55 degrees. Here we can see the phugoid for a small disturbance. The approximate time period between the disturbance and it reaching equilibrium again is 35 seconds, therefore the frequency is approximately 0.029 Hz. Longer disturbances will give larger time periods and therefore smaller frequencies and smaller damping ratios. And that concludes the briefing.